Hello friends, welcome back to my channel. So this is the part second of Hui book, and in this chapter we will going to discuss Vsepr theory in more detailed way. I have already created a video on Vsepr theory, but this time I will discuss certain important points, right? And then we will discuss Bent rule. So it was delayed in uploading this video because I have some certain health issues. So first thing is that how we can find out the shapes of molecules, geometry of molecules using the Vsepr theory. So first thing is that you have to first you have to identify the hybridization of central molecule, and we will use this formula. There's half of valence shell electrons around central metal atom plus number of monovalent atoms minus cationic charge plus anionic charge, right? We will use this formula to find out the hybridization of, then we will decide that what will be its structure depending upon the presence of lone pair of electrons, right? So this is very simple example, so I want to start with simple and then we will move to the little bit different examples, little bit difficult examples. So so first is this ClO3 minus, right? So central atom is chlorine and it has 7 electrons. Then we don't have any monovalent atom present in this molecule, so we will not take this, it will remain 0. Plus anionic charge is 1, so it will become 7 plus 1 divided by 2 is 4. 4 means it will be sp3, right? 2 for sp, 3 for sp2, 4 for sp3, and so on. 5 for sp3d, 6 for sp3d2, and 7 for sp3d3, right? And we all know the basic geometry of all these hybridization. This is linear, this is triangular planar, this is tetrahedral, pentagonal, bipyramidal, octahedral, and it will have pentagonal, bipyramidal. So we will see the how these lone pair of electron can cause variation in the basic geometry of the molecule. So it should have sp3 hybridization, means it should have this geometry of tetrahedral, but chlorine has 7 valence electrons and 1 is provided by this, so total is 8, right? And 6 are used in bonding with this oxygen, right? So remaining 2 will act as lone pair of electrons or non-bonding electrons, so it will cause repulsion in the structure and it will have pyramidal structure. Due to the presence of this lone pair of electrons, it will have pyramidal structure. Then we have XeO3. So again we will apply the same formula, that xenon has 8 valence electron, there is no monovalent atom, no charge, so we will have again 4, means sp3 hybridization. Again this xenon has a lone pair of electron and it will cause its structure to be pyramidal. Then we have SO3. So in SO3 valence electrons are 6, there is no monovalent atom, no charge, total is 3, means it will have sp2 trigonal planar structure. So the correct answer will be first one, right? So this is very easy example, we all can do this type of example. We will see what type of exam questions can be asked in the examination, and then we will see the limitations of this theory. Next question is also from December 2017, and in this they are asking us the geometry of SnF3 and XeF2O2, right? So in this the central atom is nitrogen. So first we will try to find out the hybridization of it. Half of central metal atom has 5 valence electron and the monovalent atoms are 3 in number, no charge, so it will have 4. 5 plus 8 divided by 2 is 4, and it means it has sp3 hybridization. sp3 means it should have tetrahedral geometry. Then we have XeF2O2. So central metal atom is xenon, valence electrons are 8 in xenon, monovalent atoms are 2, total is 5. 5 means it should have sp3d. sp3d means trigonal bipyramidal. So the correct answer should be fourth tetrahedral and trigonal bipyramidal. This one is also very simple. Next question is from GATE 2020. So question is, among the following species, one that has pentagonal shape. So first we will try to find out hybridization of all the molecules, right? So in this case, half xenon having 8 valence electrons, monovalent atoms are 4, it will have 6 means sp3d2, means it should have octahedral geometry. It should have octahedral, but actual structure is not octahedral in nature, because xenon has these 4 electrons are used in sigma bonding with fluorine. Oxygen will form double bond with xenon, and it will have lone pair of electron which will be present at this position, right? So it will have square pyramidal structure, so it will not be pentagonal in shape. Then IF5, so half of 7 plus 5 means it will again have 7 plus 5 is 12 divided by 2 is again 6, means sp3d2, and it should have octahedral geometry, but it is again not octahedral because of the presence of one lone pair of electron, so it will again have a square pyramidal structure. Then we have SF5 negative, so half of S has 6 valence electrons, 5 monovalent atoms plus 1 due to anionic charge, so total will be again 6, means it should have sp3d2 hybridization, but it has this one lone pair of electrons, so it will be again square pyramidal in nature, right? Then we have this xe5 minus, so it has 8 valence electrons, 5 is the number of monovalent atom plus 1, right? So 8 plus 6 is 14 divided by 2 is 7, means it should have sp3d3 hybridization. sp3d3 means it should have pentagonal bipyramidal structure, right? But in this case, if we are placing all these fluorine in this direction in shape of pentagonal, then this xenon has 2 lone pairs of electrons, right? In starting it has 8, 5 are used in sigma bond formation, 3 left, right? And 1 is due to this negative charge, so total number of electrons which are not participating in bonding is 4, means 2 lone pair of electrons. So these 2 lone pair of electron will always try to occupy lone pair of electron. Remember this, that lone pair of electron will always try to occupy the side which is less hindered. They need more space, right? So in this case, if I will place a lone pair of electrons, suppose in this direction, so and I have placed this fluorine in this direction, suppose. So this lone pair of electron and the angle between these two will be nearly 72 degree. How? This 360 divided by 5, it will become 72 degree. And if I will place this lone pair of electron in vertical direction like this, then it will make a bond angle of 90 degree. So it has more space in this structure, so it will remain in this form, and the molecule has a structure which is pentagonal planar in nature, right? So correct answer will be D. So why I am telling you this one, that always remember that whenever you have the lone pair of electron in the molecule, it will be placed in the direction which is less hindered. It may be equatorial, it may be axial in nature, but depends upon the bond angle between the lone pair of electrons, right? So try to place it in the direction which is less hindered, which has greater bond angle. Next is, based on Vsepr theory, the predicted shape of Xe5 minus and Br5 minus respectively are. So we have seen this molecule in this question also. So it will be pentagonal planar in nature, means your first option can be correct, because in first option only this xe5f minus has pentagonal planar structure, right? So it should be first, it should be correct, but we will also check this brf5. So half of Br has 7 valence electrons plus 5 for monovalent atoms, so it will become 6. 6 means it should have octahedral geometry, sp3d2, right? But this Br has 7 electrons, 7 valence electrons. 5 are used in, these 5 are used in sigma bond formation. One is left, which will be placed like this, right? So it will have a square pyramidal structure. So first will be the correct answer. Next question is from CSIR net December 2019. The species for which the shape can be predicted by Vsepr theory is or are. So we have here 4 molecules, and they are asking us that for which molecules we can predict the shape of molecules using this Vsepr theory. So before solving this question, I want to tell you certain points from Hui, that which will tell you the important points about this Vsepr theory as well as its limitation. Out of these points, some points are very familiar to you. That first is, there will be highest repulsion between lone pair of electrons, then lone pair bond pair of electrons, then bond pair of electrons, right? This will be the correct order. Then second point, which I have already told you, that lone pairs choose the largest size. Then third point is, double bonds also behave similar to lone pair of electron, and they will also occupy the space, they will always occupy the side which has larger space. So this point will become, double bonds need more space than single bond. For example, suppose I have XeOF2, this molecule. So I will first try to find out its hybridization. It has 8 and 2, means it will be 5, right? According to 5, it should have hybridization sp3d. sp3d means it will have trigonal bipyramidal structure. So question comes that suppose in the starting I am taking this oxygen at this position and fluorine in the equatorial direction, axial directions, and the lone pair of electrons, the xenon has 2 lone pair of electrons because it has total 8. One is used here, one is used here, 2, and 2 are used here, 4. It means 4 electrons are left, 4 electrons, 4 lone pair of electrons. So these lone pair of electrons will occupy this equatorial direction, and this double bond will be placed in equatorial direction also, because in this direction there is larger space as compared to axial direction. How? If you want to calculate the bond angle between these two, it will be 90 degree, right? And the angle between these two will be 120. So if I will place this oxygen in the vertical direction, then its bond angle will become lesser, right? So it will try to occupy this place which has larger space. So the trigonal planar side has larger space as compared to the axial side. So in this case it will occupy this equatorial side. Next point is, the bond angle changes with the electronegativity of the substituent attached. Suppose I have PF3, PCl3, PBr3 and PI3, right? So if I will try to find out the hybridization of it. It will become half 5 plus 3, means it will be sp3, but because of the presence of lone pair of electron, it will have pyramidal shape, right? Then in case of pf3, this shared electron pair which is forming this sigma bond will be closer to fluorine because of its higher electronegativity, right? And because of its closeness to this fluorine, means it is away from this phosphorus, the lone pair of electron, this lone pair of electron can occupy larger space, means, or you can say that the bond pair lone pair interaction is decreased. In this case, their interaction is decreased, so repulsion will be less. Now this lone pair can expand in larger space, right? And in this case, suppose I am taking here PBr3. So in this case, the lone pair of electron will be close to, the shared pair of electron will be close to phosphorus, means this lone pair bond pair repulsion will be there, and this lone pair will not expand too much, so the bond angle between this will be larger. So the correct order of bond order will be like this. The next point is that this Vsepr theory also has certain limitations. So it cannot predict the structure correctly of these compounds XeF6 and SbX6, where X is your halides, chlorine, fluorine, bromine, iodine. Similarly, this tellurium halide, bromium, Brf6 minus, it cannot predict its structures. It cannot predict their structures, right? So if they are asking you that the structure of these compounds can be predicted by Vsepr theory or not, so you have to choose the point that they cannot, the Vsepr theory cannot predict their structure. Similarly, that compounds of transition metals, the shape of transition metal halides or halides cannot be predicted by this theory, and ionic compounds are also, the shape of ionic compounds is also not predicted by this theory. Right, now we can do our question that the species for which the shapes or geometry can be predicted by Vsepr theory is or are. So first option is this platinum chloride, so its structure cannot be predicted by this Vsepr theory. Again, second one is this TeCl2 minus, which is given here, so we cannot predict its structure due to using this Vsepr theory. And we can predict the structure of PF3SF6, right? So correct option will be option number 3, C only. Then why we cannot predict the structure of or the geometry of these molecules? Because in these cases the lone pair of electron is stereochemically inactive in nature. Inactive means it will be placed in the s orbital and it will not participate in structure prediction, right? It is inactive in nature stereochemically, so it will not participate in structure prediction. So we cannot determine the correct shape of these molecules using this theory, right? So try to remember this point, this is very very important. Then next is match the appropriate geometry on the right with each of the species on the left. This question is very good, it is from June 2019. So in this case, first we will try to find out the structure of C and D. So XeO3, I have already done this one, that half of 8, there is no monovalent atom, so it will be 4, means sp3, but because of the presence of a lone pair of electron, it will be pyramidal in shape, right? So option number C will go with second, pyramidal. Then we have D, XeOF2, so we have already done this one here, it will have T-shaped structure, right? So it will go with T-shaped, it should be trigonal bipyramidal, but these lone pair of electron will be placed equatorially, and in this way shape will become T-shaped, right? So option number D will go with third. So we can have C with second and D with third, which is in option 1, 3 and 4. Only option number 2 can be neglected. Then we will try to find out the structure of A. So to predict the hybridization of A and B, we will not apply our general formula that we are using so far, that half of V plus M minus C plus A. We will not apply that one. We will try to find out the hybridization using different approach. So first we will try to draw its structure. The xenon will be central metal atom, then it is bonded with this oxygen, and this oxygen is bonded with this group OSO2F, right? And here we have fluorine. It has a structure like this. Then we will try to find out its hybridization using a different formula, that number of sigma bonds plus number of lone pair of electrons, right? So here we have two sigma bonds attached with this central metal atom, so we will write here 2, and the number of lone pair of electrons. So this xenon has total 8 electrons, 8 valence electron in the starting. 2 are used in the sigma bond formation, 6 will be left. 6 electrons means 3 lone pair of electrons, right? So we will write here 3. Total will become 5. 5 means it will become sp3d, right? It should have trigonal bipyramidal structure. Next we will try to draw its structure in trigonal pyramidal form. I have already told you in the starting, in the Vsepr theory points, that lone pair of electron will always try to occupy the site which has more space, larger bond angles. So in trigonal bipyramidal shape, this equatorial this trigonal shape has bond angles 120, while this axial shape has 90 degree. So in this case lone pair are more free to move, so they will go in the equatorial direction like this, and this fluorine and this oxygen bonded with this OSO2F group will go in axial direction, right? So in this way it will have a structure almost linear in shape, right? So it should have linear structure, means A will go with linear 1. Then we will try to find out the geometry of B. Again we will apply the same formula. Why I am using this one, not the previous one? Because if you use the previous one, this one, then you may be confused and your hybridization can be wrong. You can also apply this formula in all the examples. In previous examples also you can apply this one also, right? You will get the same result. So let's come back to our question, that in case of B you will have a structure like this. This is attached with these two groups. So again we will try to find out the hybridization. It will be number of sigma bonds are 2. Number of sigma bonds, always count the sigma bonds which is attached with the central metal atom. So it will be 2, and the lone pair of electrons are again 3. So it will also have this hybridization sp3d, right? So it will, the same thing will be applied here. The lone pair of electrons will occupy the equatorial sites, and the axial sites will be occupied by this fluorine and this nitrogen. So it will also have the structure linear, right? So your correct option will be in which the C is with second, D with third, and A and B are with 1 1, means option number 1 will be correct option, this one. So concepts is very easy, but when you apply in the examples it may create problems. So try to remember the points which I have discussed so far, all these points, right? Number of these numbers will tell you the geometry. Then depending upon the lone pair of electrons your shape can vary, right? This will be the, these all points are very important, so try to remember all these points. And if you want to go in the very basic of this Vsepr theory, that how the lone pair of electrons will affect the shape of your molecule, means when we have predicted geometry is octahedral, but because of the presence of lone pair of electron, geometry will become square pyramidal. Then you can watch my previous video on the same theory, the Vsepr theory, or you can study Puri, Sharma and Pathania, in which a table is given, and in the table all the shapes are given, that due to the presence of lone pair of electron what will be the shape, right? So this is all about the Vsepr theory. Then we will move to the Bent rule. So there is question from December 2017, that according to Bent rule, for p block elements the correct combination of geometry around the central metal atom and position of more electronegative substituent is. So before solving this question, we will take very basics about this bent rule, because in future there may be lots of questions from this concept, because this concept is very interesting, and in IITs and in IIT GEM this question is very common, right? So first we will try to understand the basic concept of it. So first we will write down all type of hybridization that we have: sp, sp2, sp3. Suppose we are taking only 4. In all these, the order of s character is this one. When we are moving from right to left, means in this direction, s character increasing, right? S character increasing means electronegativity increases, or you can say this s orbitals are more closer to nucleus, that's why electronegative character of these orbitals increases, right? Means when we have larger s character, there the electronegative character of hybrid orbitals will be larger. Means they will try to bind with more electropositive substituents. So we can generalize a thing that orbitals with more s character will be directed towards more electropositive substituent, or you can do vice versa of it also, that orbitals with lesser s character will be directed towards less electropositive or more electronegative substituents, right? So try to remember only one point, other will be reverse of it. Or you can say another thing also, that orbitals with more p character, when you have less s character, p character will be increased. So orbitals with more p character will be directed towards more electronegative substituent. This will be also reverse of the first this statement. So you can remember this one only. Then next point is, which will help us to understand this bent rule, is the first one is this. Second one is the p orbitals have higher energy than s orbital. Then we will come to the molecules with trigonal bipyramidal geometry. Most of the time this bent rule applies on these molecules. So in this case we have trigonal bipyramidal geometry, means you have sp3 dehybridization. This sp3 dehybridization is formed when you have s, px, py, pz and dz square. By combination of all these orbitals you will get sp3 hybridization. So we can divide these all orbitals in two categories, this one and this one. This spxpy means this sp2 will be responsible for formation of this trigonal structure. These all bonds are called as equatorial bonds, right? And this pz dz square is responsible for formation of your axial bond. Okay, so we have two things here, two type of orbitals are involved. These three are equivalent in energy and these two are equivalent, but these two are different from these three. So one more important point is here, that sometimes you have heard that in case of hybridization equivalent energy orbitals are formed, but it is not true for the trigonal bipyramidal structure. Here we have two non-equivalent energy, the orbitals of non-equivalent energies for here we have orbitals of non-equivalent energies, right? So it is also possible in case of hybridization that you will generate non-equivalent energy orbitals, right? So when you are forming these bonds, these equatorial bonds are shorter in size means their bond length will be low, and it means they will be strong. And axial bonds are larger in size, means they will be their bond length will be larger and they will be weak. So this is very common concept. We all know about this, that axial bonds are larger than this equatorial bond. When we have a modified question based on this concept, we may be confused. For example, suppose they are asking you that in case of PCl5, when you are heating it, when you are heating PCl5, then which type of Cl will be removed? Means when you are drawing the structure of PCl5, it will be trigonal bipyramidal. Means 3 Cl will have same bond length, while these 2 Cl will have different bond length. Their bond lengths will be larger because they are axially placed. So when you will heat it, these two will break first and you will get PCl3 and Cl2. So you have to choose the point where it is given that this axial bond will break first. So this is very important point. So from this first point we can give our bent rule. What this rule says, that the hybrid orbitals which have more s character will be directed towards more electropositive substituent, or you can say that hybrid orbitals with less s character will be directed towards the more electronegative substituent. We will take few examples, then it will be more clear to us. For example, suppose I have CH3Cl and CF3Cl. So in this case, what will be our geometry? It will be sp3 hybridized. It will also be sp3. So suppose we are drawing its structure like this. In two cases, they are asking us that what will be which molecule will have higher bond length, higher CCl bond length. So in first case, if you are looking at these substituents, Cl will be more electronegative than hydrogen, right? And this carbon has sp3 hybridization, but because of the higher electronegativity of this Cl, the s character of this sp3 hybridized orbital which is forming a bond with this Cl will be decreased, because higher s character means it will be more electronegative, and if we want less s character means it can combine with more electronegative substituent. You can see this point, that more s character will be directed toward more electropositive substituent, means more s character of these sp3 hybridized orbitals will be directed towards hydrogens, and the Cl will have this more p character. You can say that it will have more p character. So more p character means your CCl bond length will be higher as compared to CH bond lengths in this molecule. Then we will come to CF3Cl. In this case, fluorine is more electronegative than Cl. More electronegative means, or you can say that chlorine is more electropositive than fluorine. So the orbitals which have higher electronegativity will be directed towards the Cl, means the orbitals, the hybrid orbitals with more s character, will be directed towards Cl. And you know that this s orbitals are close to nucleus, means CCl bond length will be less in this case CF3Cl, right? So you can say that the CCl bond length will be higher in case of CH3Cl as compared to CF3Cl. Let's take one more example. Suppose I have methane here. All the bonds are substituted with same type of substituent, means all will have same sp3 character. There will be no higher s or higher p character, means all the bond angles will be 109 degree 28 minutes, like this. And one thing also you should know, that when we have sp hybridization, bond angle is 180, and when we have sp2, bond angle decreases, sp3 bond angle further decreases. Why I am telling you this? That when s character decreases, bond angle decreases, right? So in this case all the substituents are same, so bond angle is also same. But suppose if I have F here, right? So in this case this fluorine has higher electronegativity than hydrogens. So higher electronegativity means it will attract the orbitals which have higher electropositive character, and p orbitals have higher electropositive character than s. S are more electronegative in nature. So the p character of sp3 hybridized orbital will be shifted towards fluorine, means is its percentage s character decreases. You can say percentage p character increases or percentage s character decreases. And we know that when s character decreases, bond angle decreases. So this bond angle will be less than 109 degree 28 minutes, and it will be greater than 109 degree 28 minutes. Why it is greater? Because here s character decreases, so to balance it the s character will increase in this side, right? So the bond angle will increase in this side. So this concept is very very important. So I think this topic will be clear to you, and try to remember the important points about both the concept. Vsepr theory is very very simple, we all know about it, but in future examinations they will ask you some tricky questions, right? And in bent rule also the concept is very simple, but these questions can sometimes confuse you. So try to revise them, and if you like my videos please share my videos with your friends, and thank you so much for watching.